So let's start last lecture of Ilya Dumanski from MIT, Perverse coherent sheaves on symplectic singularities. Ilya, please.
Okay, thank you again for the invitation. So let me remind that in the first lecture we discussed the notion of perverse coherent G-equivariant sheaves and considered two main examples, the nilpotent cone and the affine Grassmannian. And I tried to overview known results about this category in these two cases. In the last lecture, we define symplectic singularities, but today I'll remind this definition, and then we spent the rest of the lecture discussing the algebraics and modules over them, and in particular we gave some description of the category of modules over a transitive Lie algebroid in holomorphic setting or in analytic setting. Okay, and so today we will combine these things. We will define the notion of perverse coherent sheaves on symplectic singularities, homogeneal and Poisson varieties under certain assumption, and I will try to say what is known or expected about this notion. Okay, so more precisely, this is the definition introduced in the first lecture. I actually have not introduced it. It was introduced by these people. And let us again briefly recall that that definition was that we had an algebraic group acting on a variety with a finite number of orbits, and dimensions of adjacent orbits should differ by at least 2. And then we impose on an element of the derived equivariant category of coherent sheaves the following two assumptions: that for every orbit, its star and Schrick derived pullbacks on this orbit lie below and above certain homological degree. And then some sort of miracle is that this category is abelian and Artinian, and simple objects can be classified as IC extensions of simple objects from G orbits. So yeah, let me make an obvious observation that simple G-equivariant coherent sheaf on a G orbit is the same as representation or simple representation of a stabilizer of a point on this orbit, which is explicit and computable in a lot of cases. All right, and now this definition is great, but the problem is that there are not so many examples satisfying these assumptions. And our idea was to try to generalize this notion to symplectic singularities, following an idea introduced by many people, actually, that a lot of stories in representation theory should be possible to generalize to this setting. And let us again recall the definition. We call X a symplectic singularity, or, well, again, here I'm a little bit cheating. I'm defining symplectic resolution. That's a bit stronger, but for simplicity, it's okay. The definition is that X is a symplectic singularity if it's a normal Poisson affine variety, and it admits a projective resolution of singularity by a smooth symplectic variety, and the morphism of resolution should respect Poisson structures. And so let us recall examples. It is the nilpotent cone resolved by the cotangent bundle to black variety. Those are Kleinian singularities, which are plane singularities classified by types AN, DN, EN, E6, E7, E8. It is the resolution of by Hilbert scheme of the symmetric power of C2. And I mentioned that there are examples like Nakajima-Quiver varieties, Coulomb range, which I will not use and will not define. And another thing I mentioned was slices in affine Grassmannian, but I did not need it last time, but today I actually will use them. So let us define them. Right. So let us take. Remember when I spoke about affine Grassmannian, I said that the g of t action on it on the affine Grassmannian, the orbits are labeled by dominant co-weights. So yeah, let me take again dominant co-weights of G. Then there are some representatives in orbits called T lambda check and mu lambda check. Let us define them. So co-character, by definition, is a morphism from C star to Cartan torus of G, which is the same as which can be thought of as an element T lambda check inside T of T plus minus 1. And so this can be naturally mapped to the affine Grassmannian. So this indeed can be viewed as a point in the affine Grassmannian, and the point is that these points are representatives of orbits corresponding to this co-weight. So orbits of this point, when lambda and mu are dominant, do not intersect, and they are all do not coincide, and they are all the orbits present.
So, yes. Sorry, Ilya, of course, there are people who like representation theory, but for those who do not care, let G be GLN, all right?
Okay.
So yes, then it has a very transparent answer, but maybe you will tell what it is.
Yeah. So then the Cartan torus is just the space of diagonal matrices inside GLN. Well, basically that just we have a homomorphism to this torus here can be just represented by, so T lambda check is just T lambda 1 dot T lambda n. This point inside this group, and we take its image in the affine Grassmannian. Yes, so in this case, this is very explicit. Thank you. Right, so this is inside GLN of T plus minus 1. Right. Yes, and then again, there is this group, G of Laurent series. And the idea kind of is that we can take the opposite group, the, so to say, transversal group, which is denoted G1 of T inverse, and is defined as the kernel of the evaluation map from this group to G. So they are matrices. Again, if GLN, you can think that they are matrices n by n, invertible, with the coefficients in with coefficients being polynomials in T inverse, and such that if we kill T inverse, tend T to infinity, if you wish, we get the identity matrix. Okay, so it's kind of the opposite group, the transversal group to this one inside the whole loop group. And the idea is that we take a closure of this thing and intersect it with the orbit of T mu inside the affine Grassmannian. And this is transversal slice to one orbit inside another orbit. And it turns out that it is a conical symplectic singularity. Okay, so conical.
Is it obvious?
It's not hard. Well, so first of all, where does the Poisson structure come from? That's. I apologize to those who don't care about representation theory, but like there is a general theory of quantum groups or Lie algebras, and there is a notion of Mannian triple, and the following thing forms a Mannian triple G T inverse. So those are kind of dual.
Maybe T minus 1. What? It's not.
Oh, sorry, is the order incorrect?
No. I mean that the if you take gt minus 1, I would multiply it by t minus 1.
Yes,
They
yes,
should
you're
not
absolutely right.
intercept.
Exact, yes. So yes, that's a kind of t, yes, which can be denoted in parallel to this notation g1 of t inverse. Yes, thank you. Right, so this is these are this Lie algebra. That's its dual, and that's the so-called double. And then from general theory of Poisson Lie groups, it follows that on homogeneous space like this, there is a natural Poisson structure.
Yeah, for those, still there are some people in the audience who do not care about representation theory. So the first space in this triple is a direct sum of the other two, and the first space carries sort of an odd symplectic structure given by the residue of the pairing. Imagine that it is GLN, so it's like residue of the trace of the product of two series in T. So, and the other two are just Lagrangian subspaces with respect to this odd symplectic pairing. So, and it's not a very mysterious thing.
Yeah. Thank you. Right. Yeah. And so, yeah, the Poisson structure comes from this, and it's also a general theory that symplectic leaves of such a Poisson structure would be basically precisely, well, if I wouldn't take closure here, I would take just intersection of two opposite things. That would be precisely symplectic leaves of such.
Yeah, but the question is why it's conic symplectic
Conical
singularity.
Yeah. So the part about symplectic singularity is somewhat technical, and the conical. Let me just say that, as maybe I mentioned in the first lecture, there is the loop rotation action, which scales the t variable. So some s inside torus maps t to st. It's called loop rotation because it's like just if you can see this thing as a loop group, this torus just rotates this loop. Yeah, and well, this thing is already conical, right? Because by definition, it's a kernel. So this kernel contracts to the identity in this group by this action, and we intersect it with some closed subscheme, so it remains conical. This closure contains this conical point, attracting point. Okay. Right, so that was the definition which I will use later. Now let's return to the setting of arbitrary symplectic singularity. Then it is a theorem of Dmitry Kaledin that X has a finite number of symplectic leaves. And note that obviously by construction the dimensions of symplectic leaves are even because they're symplectic. Yeah, so this stratification looks, at least at the first glance, suitable for the definition of perverse coherent T structure, but we don't have a group which acts transitively on symplectic leaves. Instead, by the very definition, we have a Lie algebroid which acts transitively on each symplectic leaf. And that was one of the examples of Lie algebroid yesterday. So we consider the cotangent sheaf of one forms, and the Poisson structure on X equips this sheaf with a structure of Lie algebroid. And the Lie bracket is determined by this condition, and the anchor map is just the Poisson pairing, Poisson bivector map. And we can consider the category of Poisson sheaves or Poisson modules on X, which we will denote like that. And so yeah, that is why it seems reasonable to define the notion of perverse coherent modules over Lie algebroids. So instead of transitive action with finite, not transitive, with action of a group with finite number of orbits, we can consider a Lie algebroid with a finite number of orbits, also satisfying this.
Excuse me, just a quick. So this omega, this first is a Poisson module, Poisson sheaf, and also together with the Lie algebroid action, which consistent with the anchor map.
Yes. So what's the question?
The question is about the very quick on this Koch omega x.
Yes.
So first
what is the definition or the definition? Yeah. So
Poisson sheaves, which has nothing to do with the algebroid, but the algebroid also acting and consistent with the.
No. So Poisson sheaves, by the very definition, are it's written here. Poisson sheaves, by the very definition, are modules over this Poisson Lie algebroid.
Oh, I see. That's what you. And basically, I could think of any Poisson manifold. I can look at the Poisson modules of the function of the structure sheaf.
So they are modules over. Okay. Let me maybe give.
So because the structure sheaf, you have a Poisson structure which has both the module structure and also the Lie algebra. That's a different Lie algebra action, which is irrelevant to this omega.
So at the moment, I don't have any Lie algebra action assumed. So X is just a Poisson.
Here, X is a Poisson manifold variety.
Yes.
Am I right?
Yes.
So its structure sheaf has a Poisson structure, which is a Lie algebra. So what do I mean Poisson sheaf here?
Well, yeah. You can say that so it's if you would assume that you can take commutate, you can multiply by function. If you have a sheaf, you can multiply by function, and you can take a Poisson bracket with a function that will give you precisely the same datum as the structure of module over this Lie algebroid.
Because now you have in addition to the Poisson structure on the structure sheaf, and you have another Lie algebroid.
Yes.
Which is also acting on the structure sheaf as well, right?
Well, yes, structure sheaf is a Poisson sheaf with a natural. So that's just a different language. I think that's just a different language to.
Try to understand that what that really mean. And the language doesn't matter. Just to say you basically, I'm here have two different Lie algebras together with there is a Lie algebra action on the structure sheaf, and the structure sheaf itself has a Lie algebra structure as well.
Yes, so in this language, you can forget about the structure of Lie algebra on the structure sheaf. You can just remember that there is additional structure of Lie algebroid on this sheaf, and you can consider modules over this Lie algebroid. And that will be precisely, it will be the same as if you would assume that, it's really just the same. Yeah. So if you if you take, if you want to apply a Poisson bracket with some function, it's not the function which matters. It's the RAM differential that matters, right? And so that's just, we kind of, that is precisely the sheaf of one forms. So we apply df to your module. That's you can. So yeah, nothing smart happens here. It's just
okay. You can go ahead. Check
okay. Thank you. Thank you for the question. But yeah, maybe let me also emphasize that in case X is symplectic. So the Poisson structure comes just from symplectic form. Then the anchor map, the Poisson by vector, just identifies cotangent sheaf and tangent sheaf, and so Poisson sheaves are the same as D modules. So in particular, they do not depend on the symplectic form. So Koch well, let me say dx. Anyway, let me denote it like that. So yeah, but in general, it's a different structure. Okay, so yes, that is why. So yeah, we have a naturally algebraic which acts along with a finite stratification, and the definition, the theorem, which is not so hard, is that perverse coherent T structure exists for modules over a Lie algebraic L under the same assumptions as for the group case. So the assumption were that finite number of orbits and dimensions differ by at least two. For example, they are all even dimensional. If they're all even dimensional, that is automatically satisfied.
So, which means that it's also abelian Artinian.
Exactly. Yes. Yes. The same.
And you work in algebraic category.
Yes. Yes. I work in algebraic category.
Okay, like Zariski topology.
Yes. Yes. So then the very much same definition applies, and the conclusion is also the same. The category of sheaves. So let me make a quick remark that I skip some technical details. For example, here I actually did not specify. I could consider just the derived category of coherent sheaves, or say I could consider the derived category of quasi-coherent sheaves with coherent cohomology. And there was no difference in the group equivalent case. These categories are equivalent. But that's not the case for the case of Lie algebraics, even over a point. So for over a point, Lie algebraic over a point is just a Lie algebra, and there's even for semi-simple Lie algebra over C, it is not true that these two categories coincide. So I skip these details. I don't specify in which of these categories I work because there are some new technical details. But let's skip it unless there is some particular interest in these technicalities. Right. And also there is the functor of IC extension, which means, again, that simple objects in this category of perverse Poisson sheaves, or perverse coherent sheaves, or perverse coherent modules over L, they are parameterized by pairs an orbit of this Lie algebroid and a simple L module on O. And okay, yeah, and again, there is some canonical way to extend it to the whole category. Right, and so note that now this thing is transitive on orbit by definition of orbit. And in the group equivalent case, there was no difficulty in describing what this is. And in the Lie algebroid setting, it is somewhat less clear. Right, and last time I gave some description of this category in the analytic setting. And yes, here I work in algebraic category. So we have the nullification functor, of course, so we can analyze it. And that's what I'll discuss if I'll have time today in the end of today's talk. Right, and so this theorem allows us to give the following definition. If we have a X now is a symplectic singularity again, this is our Poisson Lie algebroid on the sheaf on the cotangent sheaf, and we define the category of perverse coherent sheaves on X as the category of perverse Poisson modules over this Lie algebroid. And let me make a remark that I personally am mostly interested in symplectic singularities at the moment, but this definition works for any Poisson variety with finite number of symplectic leaves. Yeah, so I haven't looked at it in some examples, but yeah, in particular, there should be some canonical simple objects, so simple Poisson sheaves on any such example. I don't know if anything nice can be said in this generality. Okay, but let us return to the examples which we considered on the first talk. So the first example was the nilpotent cone inside some, let's say, simple G. And now we have some kind of problem because we already had an existing definition of equivariant perverse coherent sheaves on N. And now we have some new definition which is applicable in larger generality of perverse Poisson sheaves on N. And it turns out that these categories, these definitions are actually different, but not that different. So they are very much related. So let's look into that. Okay, so we have the action of the Lie algebra G. This is the anchor map for the we have the anchor map for the infinitesimal action of G on N, and we have the anchor map for this Poisson action for Poisson structure. But now, basically, by definition of a Hamiltonian action, G acts on the nilpotent cone Hamiltonianly. That means that there is such a map, so that this triangle is commutative. Yeah, and actually it's easy to see that here it's surjective, just because this is a closed embedding. Oops, this is a closed embedding, and yeah, this follows that this map is surjective. Okay, so in particular, given a Poisson sheaf, we can restrict it to G equivariant sheaf along this map. Right, so let me take G to be simply connected for simplicity, and there are variants of this theorem for a non-simply connected group. Then let me just say that then you kind of need to consider modules of a Harish-Chandra pair, so module over this algebraic such that it is integrable with respect to some quotient of simply connected group. But to avoid this, let me just assume G is simply connected. Then there is, so as I said, there is a functor which from Poisson sheaves to G equivariant sheaves.
I do not understand the notation, because you have two upper indices. C star and omega n. I forgot whether. Yeah.
Right, thank you. So we also had the contracting action on N, contracting. And again, for simplicity, it's just a little easier to state this result in the case of graded categories. So I consider graded Poisson sheaves. Graded means equivariant with respect to this C star. Okay?
And all the definitions kind of, they go through,
yeah? Yeah. So, well, actually this...
And this is why, because the C star action is compatible with the Poisson structure or what?
Yeah, something like that. So in here I kind of skipped it again for simplicity, but there is a notion of Harish-Chandra Lie algebroid, meaning that you have a Lie algebroid and the group, and you can consider modules kind of simultaneously equivariant with respect to these things. And this theorem holds not only for Lie algebroids, but for Harish-Chandra Lie algebroids as well. That's no problem.
Okay.
And yeah.
So C star is that group. Yeah.
Yes. In this case, yes. And as I said, in case you want to get some result about non-simply connected group, then you need to add also the condition of integrability along this non-simply connected group. But for simply connected group, it's automatic. Right. So I mean, here you need to add it. Right. So yes, we have this functor of restriction, and the first claim is that it restricts to a functor between categories of perverse coherent sheaves. So it respects these T structures. There is such a functor. The second claim, which is kind of implicit here, is that this functor commutes with IC extensions from orbits, and it maps simples to simples, which is, let me comment while I'm stating the theorem, this part that it maps simples to simples is not hard, basically because this map is surjective here. Let me define it phi. Then, of course, the restriction along a surjective map, the restriction of simple is simple. And the slightly harder part is that it defines a bijection on the isomorphism classes of simples. So any simple sheaf here actually comes by restriction along this map. So hence it induces an isomorphism of Grothendieck groups, which preserves Poisson basis. So here K with this index means just the Grothendieck group of this category of graded Poisson sheaves. Okay, so yes, so
and the question about cluster structures in general, it's extra. It should be.
Cluster structure appear in the case of affine Grassmannian.
Yeah, but I mean that this kind of, it cannot be derived from any general result. It should be worked out individually.
Which result?
Well, about the fact that the perverse basis gives you the classes of perverse basis give you cluster coordinates on the K group.
So first of all, again, this theorem is about the nilpotent cone, and so here I don't know any.
I would ask about more general Poisson manifold, not just about.
Okay, sorry.
Question about no. I mean it's a question about generality. So if it's specific to affine Grassmannian, then probably it's something very special about it. It's well, I mean that whether you can kind of reprove this Coutis and Williams result about
So I cannot, but so I think that in all known examples, if there is a monoidal cluster categorification, then classes of simples give these functions common triangular basis in the corresponding cluster algebra. Yes, to this I don't know a counterexample, and I don't think there exists a proof.
Okay.
Yes, that's a great question, but I'm not an expert, unfortunately. So yeah, I think in all known examples this holds. For example, there is big story of Hernandez and Leclerc, and about cluster monoidal categorifications for modules over a quantum affine group, and there in all related examples it also holds, as far as I know. Right, but here I don't know about anything cluster, but oh yeah, sorry, I wanted to make the following remark. So these two categories here, they are different, but kind of the sets of simple objects are the same, but the kind of X are different. Extensions in these categories are different. And you can think of analogy, and this will be actually implicit here. I will explain it here. So if you have a two algebraic groups, and one is quotient of the other by a unipotent subgroup, then again simples are the same, but X are different. Okay. Right. So and here this basis of simple objects gives the Kazhdan-Lusztig canonical basis in this space, as I tried to outline in the first lecture. So this basis, which appears in this construction, is the Kazhdan-Lusztig canonical basis. Okay, so let me illustrate this theorem for two particular orbits. So first, let's consider the easiest orbit, g-orbit there is in the nilpotent cone, which is just 0. Then what are simple objects in these Poisson categories? Well, by the very definition, they are modules over the fiber of this Lie algebroid at 0, which is a Lie algebra. It's always the case if there is symplectic leaf, which is a point, the cotangent space at this space, this point is a Lie algebra. And in this case, it is not hard to see that this Lie algebra is just G. So simple objects are precisely G modules. And that agrees with what we have here, which are also G modules. I assume that G is simply connected, so they are the same. Finite dimensional modules are the same. Okay, that was an illustration of the theorem for the easiest possible orbit. And for another orbit, let us consider the open orbit, the opposite example, the open orbit, regular orbit. Then let us consider what happens in the G equivariant category in this case. So it is well known, or again, to those who are not interested in representation theory, it can be seen for SLN. It's very explicit. For other types, it also can be seen that the stabilizer of group inside grouped of a regular nilpotent, its connected component of identity is unipotent, which means that on every simple G equivariant module, the action of G of the stabilizer factors through the quotient by this unipotent. So it now what it means at the level of Lie algebras, if the connected component of identity acts locally, like acts trivially on V, means that the action of the Lie algebra locally factors through this morphism to the tangent space along this regular part. And now, as I explained before, on the symplectic part, on the regular locus, the nilpotent cone is just symplectic. So Poisson sheaves are the same as the local systems and vector bundles with flat connections. So we indeed see that on any simple G equivariant sheaf, any simple G equivariant sheaves, it comes from this Lie algebroid. So again, we see that simples are the same. Okay, and for general orbit, it's a generalization of this argument. One can check that the stabilizer inside G factors through to the kernel of this anchor map, and this quotient is a quotient by a unipotent subalgebra. So simples are the same. Okay, so let me now go to the second example, which we considered in lecture 1, and treat it now how it can be related to this new definition. So again, let me, for simplicity, assume that G is simply connected. Then remember I defined slices in affine Grassmannian, and in case G is simply connected, actually affine Grassmannian in this case is connected, and you can always take a slice to the zero orbit. So there is a T0 orbit, which is just the point inside the affine Grassmannian, and you can consider this transversal slice to this small orbit, and it will be open in this Schubert variety. Okay, so now a statement which is analog of the above theorem for the nilpotent cone is that there is the functor from this category of perverse Poisson sheaves for this open slice to the category of G times G of T equivariant coherent sheaves on the affine Grassmannian. So this is the old definition of group equivariant perverse coherent sheaves. And again, it maps simples to simples. And now it defines on the level, if we fixed lambda here, it defines only an injection on isomorphism classes of simples. So we have an injective map which preserves perverse basis. But the important part is that it becomes an isomorphism when we enlarge lambda check. So what this means? This means the following. Let us fix some U check, and a simple on simple perverse coherent sheaf on the affine Grassmannian is which is of this form. It maybe doesn't come from this slice, but it does come from some larger thing. So note that kind of when we enlarge lambda, we have a surjection. So now we consider modules over this Lie algebraic, and when restricted to a smaller subvariety, it's now maps surjectively to what we had before. And in particular, we have a larger, so to say, stable kernel of the anchor map, so which should be thought of as the stabilizer of this Lie algebraic action, and we kind of more object could come. And so the statement here is that any object supported, simple object supported on mu, comes from some maybe larger lambda. And so in particular, if one is interested in the whole affine Grassmannian and not on so its part, which is, I would say, a reasonable thing to do, then the kind of the whole perverse coherent basis comes from this Poisson construction. And let us also recall that in this case, also this basis, so for GLN, it coincides with Lusztig's dual canonical basis. And for in other types, it is, that's what Jan asked about, it's expected to be some certain canonical basis in the cluster algebra under the validity of conjecture that this covariant K theory is isomorphic to a cluster algebra. And more, yes, it is a cluster, monoidal cluster categorification. Yes?
Yeah, first of all, yeah, I mean, the one which includes a group, it's Coutis and Williams category of what?
Yes,
when,
yes, yes,
when
yes.
When you take the limit, I mean.
Yes, 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 exactly, yes.
So your category, what I do not understand, in the limit, is your category equivalent to Coutis and Williams, or there is only whatever faithful functor which is bijection on simple objects?
The second option.
No, I mean, second,
yes.
There are two things. One, you use
Yes.
the group itself. The other one, you use the Lie
Yes.
algebraic, all right? So in general, these are two different things, but in example, like nilpotent cone, you demonstrated that there is a bijection on the level of simple objects, and so isomorphism for K theories, whatever, yeah?
So
Okay, good. Now, for affine Grassmannian, you have the group, and this category of perverse coherent sheaves. It's Coutis and Williams category, which carries also monoidal structure and some meromorphic R matrix. Now, when you work with category of modules over algebraic or whatever, Harish-Chandra maybe, Does it have all the same structures as Curtis and Williams category?
Yes. So yeah, I think now I understand the question. Let me answer it. It's a great question. So let me add the page. Sorry, how do I do that? Yeah. Okay. So yes, if I take the limit, then I should consider the following thing, which is an open subset in affine Grassmannian, which is just G1 of T inverse applied to T0. And then what is, so to say, the cotangent sheaf to it? Well, this action now is faithful, so there is no stabilizer. This thing just can be identified with this group. So probably tangent sheaf should be thought as the Lie algebra of this group, and cotangent should be thought as the dual. But dual in which sense? Dual in the sense of this Manin triple, which I wrote before. So this the dual would be this G of T, and this act here, and that is precisely the Poisson, the cotangent Lie algebroid induced by the Poisson structure here, which acts on this thing. So, and in particular, this just becomes very much the same, very much similar as the group action here. So the group does not act on this open part, but the Lie algebra perfectly acts, and it precisely coincides with this Poisson construction, which I described. And indeed, the precise statement here is that if you also, so this would be not true, I think, at least. It would be not true if I wouldn't include the loop rotation equivariance. But if I do include it, then I think I can show that this is equivalence of categories.
Perverse coherent or because it's
Both,
different structure?
Both, yes.
Monoidal, what's a monoidal structure for the
That's a different question, how to describe the monoidal structure on this stuff, because it's not immediately clear to me, because, well, maybe it's okay. So I haven't thought about that carefully about the monoidal structure, so you should... well, no, it's not immediately clear to me, because here you write some convolution diagram, use some descent along this group action, and how to state the same without group action is not immediately clear to me. But, well, maybe this theorem suggests that there should be a way to state what is the natural monoidal structure here, how to rephrase it in this language.
So then if it's true, so then instead of Curtis and Williams, you can consider your category.
Yes, but, well, yes.
Okay.
But in the constructible case, from the geometric Sataki, there are monoidal structures. Is this somewhat similar to that, or?
Yeah, on the right-hand side, but not on the left-hand side.
I see. Yeah, the left-hand side. I was looking at the right-hand side.
Yeah, right-hand side, the monoidal structures in constructible and coherent worlds are defined very much similarly.
And in the coherent, in the perverse coherent case also, because the right-hand side is the group action. Okay.
Yeah. So I would actually say that this. Okay. Anyway, yes, that is correct. Yes. Okay. Right. So yes. Now maybe let me make a remark that so we see that this new construction it generalizes, maybe not to some extent it generalizes both previously studied cases. In particular, it generalizes both bases. And my expectation, which I cannot comment on anyhow precisely, but the expectation is that for general X, at least for symplectic singularities, this simple should carry some structure of canonical basis in some sense. So this can be viewed as some extension, some step toward this extension Kazhdan-Lusztig theory in this setting. So let me maybe put a question mark here. Okay. And now maybe question? No?
Well, you say symplectic singularities, but I did not really feel where you use the
No,
fact that it's symplectic singularity.
Well, since it's some question about some statement about intuition, maybe I just don't have too much intuition about to which generality this should extend for symplectic singularities. It just very often happens that many natural constructions, say for nilpotent cone, they very much similarly generalize to the setting of symplectic singularities. And to a more general setting, I'm not sure.
Okay.
But yeah, I don't have any counterexamples or whatever. Okay. So let me maybe now at the end say more about the relation to the last lecture and how it may help study the case of general X. So recall that simple objects which come from AC extension from a fixed symplectic leaf, they are parameterized by simple modules on this leaf. So we restrict this Lie algebroid that we have to the leaf. So note that this is larger than the cotangent sheaf on that leaf. For example, if S is a point, then this is some Lie algebra, which is G in the case of nilpotent cone. And so in general, it's something larger than just this thing. And we're interested, but it is transitive, and we're interested in simple modules over this Lie algebroid. But we work in algebraic setting, and last time I gave some description of this category in the analytic case. So how to compare the analytic simple objects with algebraic. So I see two options. One, which I haven't thought about actually, would be that maybe we should just make some assumption that everything, we should consider not all Poisson sheaves, but those whose restriction to every orbit has regular singularities, something like that. Then one would need to check that IC extensions of sheaf with the regular singularities would also have regular singularities. That seems probable to me, but I don't know much about that. I mean, I have not checked that. And the second option would be, which again is very often in the case of symplectic singularities, assume that X is not arbitrary but conical. That means that there is a torus contracting action with which scales Poisson by vector with a positive weight, and study graded, which means C-star equivariant Poisson modules. And note that all examples which I mentioned at the beginning of today's talk and yesterday, they are all conical. So here we have the contracting action which just scales the Lie algebra, and the nilpotent cone. Kleinian singularities are also conical because they are, well, of the form A2 mod gamma, and A2 is conical. This thing is also conical because we can contract C2 again. Quiver varieties are also conical. I will not maybe explain this. And as is explained before, we have the loop rotation, which scales the which also makes slices in affine Grassmannian conical. Right, so this is a reasonable generality. And then, so if we consider graded coherent modules over this Lie algebroid, we can, so yeah, here I assume that S is like not the contracting point of this action. So 0 is contracting to point which I will denote 0. Then we can factor by this contracting action, and we will get something projective if we apply it to the closure of a symplectic leaf. And we will also have the equivariant descent of the Lie algebroid. Oops, so yeah, here I do not have C star anymore. I killed it. Yeah, so here it should be like that. Oops. And yeah, and then we are interested not in the closure, but in a symplectic leaf itself. So note that this is projective, and this is open with complement of codimension at least 2, because the complement is a union of symplectic leaf, which leaves which are of codimension 2 at least. And it is so note that this is not smooth, but we should. So I skip some details. In fact, it's not normal, but we can take normalization. And so the outline is that for the case of open of codimension 2 in some, say, normal projective variety, it is true that any module for Lie or module over Lie algebroid has regular singularities. So in this case, algebraic modules.
But what do you call regular singularities? You somehow did not explain.
Yeah. Well, there is a well-known notion for modules of the tangent Lie algebroid, and here it's a straightforward generalization. So maybe I don't have time to explain that in full details, but anybody who knows the definition for tangent Lie algebroid could invent the correct definition for any, say, transitive Lie algebroid. So I'm my Lie algebroid is transitive on S, and I basically need that in some projective, in some compactification, its extension at every point, it's generated by something finite. Okay. Yeah, and so in this case, if we consider graded sheaves, then analytic and algebraic categories actually coincide, and this result, which I spoke about yesterday, can be applied. Okay, so that was what I can say about general case, but in general, outside of these two examples, which I explained, which are sliced to the affine Grassmannian and nilpotent cone, well, I also have some expectations for Slot-Davis slices and well, other slices in affine Grassmannian, not necessarily to 0, but outside of that, I cannot say much about this category. But I think it would be interesting to study it. Okay, it's time to finish. Thank you very much.
Thank you. Okay. By the way, any relation of these categories for symplectically dual?
That's also a great question. I also cannot say anything.
All right. So questions?
So let me ask, when you mentioned about the Harishchandra Lie algebroid, so in this case, you have a Lie algebra, and like in Harishchandra, you also have a group in Harishchandra. So the Harishchandra module will have both the Lie algebra structure and also compatible group action.
That's right.
So basically just the equivalent version. And you don't need anything as what Harishchandra is setting, that's some kind of finiteness.
What sort? No, well, what sort of finiteness? No, there is a notion of strongly coherent module over a Harish-Chandra-Lie algebroid, which means that it can be integrated to G to the group. Yeah.
So I try to get the feeling of why the name Harishchandra here.
Oh, yeah. The notion of Harish-Chandra-Lie algebroids was introduced by Williamson and Bernstein in the paper about
proof of Janssen conjecture.
Exactly. Yes. Well, and the name just comes. You have the usual notion of Harish-Chandra pairs, where you have a Lie algebra and the Lie group, and a morphism from the Lie group of G to Lie algebra of G to H, and you can consider. Yeah, that's just a generalization from.
Okay, I see. Yeah, because in that cases you don't want, and the G acting, you want to keep some kind of a semi-simplicity, so that each of the component, or you do require some kind of finiteness. Each irreducible component of group G appears in any modules with a finite. I just want to see whether you need any kind of finiteness condition on that.
Well, I think any algebraic group would work.
Yeah. I mean, it's basically it's a coherent.
Yeah.
More questions?
Okay. No more.
Can I ask a quick question just about the adjective of projective in the definition of symplectic resolution? Like, does that apply, for instance, from Hilbert of C2 to Sim-N of C2? Or do you really need that to be projective?
But it's projective for Hilbert to S2.
Yeah, well, this is definitely projective. For example, I think maybe someone else yesterday asked about queer varieties realization of this stuff, and this is by the very construction, it is projective morphism.
Okay. Thank you.
And so you said that you didn't know too much about the general Poisson framework. So certainly you were motivated by representation theory and you clearly demonstrated it. But if like the theory of D-modules, it exists without any application to representation theory. So then what's the functorial behavior of this category of modules or this Poisson algebroids? So it's kind of a natural question, but so
yeah, that's right.
Pull back, push forward. Actually, more interesting question is a blow up. So either sort of a general theory and a related question, if you have a Poisson structure, you can quantize it. Is there a quantum?
Regarding your second question, it again will be from representation theory, but I apologize. So the quantum analog of Poisson module would be a bimodule over quantization, right? And indeed, again, for the case of nilpotent cone, Ivan Losev considered the category of perverse bimodules over quantization of the nilpotent cone with the same definition. So the T structure, the T structure.
I missed bimodules over what?
Over quantizations.
Okay, good.
And you can define its So in this setting, you can define the T structure. I don't think the notion of IC extension can be quantized. Well, at least it's not obvious to me. the fact that these formulas would define T structure is sort of not hard to check. So yes, you can consider such category. Yeah, but here actually considered it in positive characteristic, and showed that in positive characteristic it is equivalent to some variant of category all, also in positive characteristic. These are a kind of Harish-Chandra bimodules, perverse Harish-Chandra bimodules. So yes, so I want to say that there is an evidence that that can be a reasonable object, again from representation theory, but some parts of theory wouldn't survive.
Okay, good. All right. So
Let me, if you're done, ask a last question.
I'm not done, but you can.
Okay.
So probably I will ask last question, but go ahead.
Okay. So I was checking through your paper, Memo 2.9, and in the Harishchandra algebraic case, you were only talking about the coherent sheaf. This is much more general X, not like a Grassmannian case.
Yes.
And says
Yes.
this has a Panachian category structure, which is very much of observed by Nick Katz. So what is the tensor structure? It's just a tensor over also OX module?
Yeah.
Okay. I'm just curious. That's the obvious one, whether there is something different. That's different from a Grassmannian case.
Yeah.
Okay. That's it. Thank you.
Yeah, Ilya, sorry, I wanted to ask you. But it's a simple question. You mentioned that you define the notion of regular singularities, yes, and probably it's completely determined by restrictions to the curves, similarly to D modules. Yeah.
Yes, I think so. Yes.
Yeah, but I'm more interested about irregular singularities because it's equivalent exactly in this Poisson story case to the choice of particular compactification. You choose compactification, and basically in the regular case, probably it doesn't mind which one you choose, just any normal crossing or simple. For irregular, this compactification, it determines irregular behavior. So then there might be, I don't know, it's either a question or suggestion to work out and to see what happened if you consider modules with irregular singularities. Because it's exactly what kind of we work out with Maxim. So, but in a sense, it involves certain blow-ups. So you should not just, after all, it's certain compactification of your symplectic leaf. Yeah, you start with a symplectic leaf, you chose this S bar compactification. In the regular case, it's also certain compactification, but we cannot see it without choosing an arbitrary compactification like S bar in your story, and then making some blow-ups. And after that, we keep only some of the divisors in this blow-up story, and only after that we consider, in your language, it probably will be this the Lie algebraic, the corresponding Lie algebraic with irregular singularities adapted to this particular compactification. And it should correspond to the theory of irregular D-modules, morally. But in your case, it will be some interesting story. Yeah, there are these interesting results about for example, Higgs bundles with regular singularities and affine Grassmannian. Yeah, like it's people around you. Like,
Yeah, that's a
GVU.
good suggestion. You said it will be an easy question.
No, it's an easy question, but I did not say that it will be the easy answer. Yes, so that's okay. So anyway, thank you very much. It's very interesting, and also for those who want to read more, there is a paper, so you can go to archive and to read more. And I ask you to send me the updated notes as well. All right. Well, thank you very much. It was
Thank
very
you.
interesting, very interesting.